All right, looks like we're off and running there. Okay, just a few things first about lab for this week, just to remember what's due and what's coming up. So first off, I think we have a quiz tomorrow in lab, and also I think there's a homework due, correct? Homework number 3 ought to be due.
Sounds about right.
Sounds about right. Good, perfect. And the other thing, just to bring to your attention, you guys have probably seen it already, is that I posted the acid analysis lab of kombucha up on the D2L. So we're going to actually start the standardization part of that tomorrow, because really we don't have a whole lot of finishing up to do with the other lab, the gravimetric one. So if you think about it, what we have left to do there is get a weighing on your crucibles with your precipitate. They go back in the oven for another hour. They come back out, they cool, and then we're going to weigh them again. So that's pretty much it. So there's a lot of hurry up and wait in tomorrow's lab. So I figured we might as well go ahead and start with the standardization of the base that we're going to need for the kombucha. So that base solution is all made up. I will have everything out that you guys need for the standardization process. I went and dug up a bunch of microburettes. By the way, have you guys worked with microburettes before? Did you do that last semester?
No.
No.
At least I didn't.
No, if you didn't, then probably nobody did. So, okay, that's good to know. So you'll get a little primer on how to use microburettes tomorrow, and we'll go ahead and start out with the standardization process. And chances are you'll probably get through that tomorrow. It's not very time consuming, honestly. Okay, so just remember, a quiz tomorrow. Homework number 3 is due tomorrow. Finish up the gravimetric lab, and we'll start the kombucha lab. So make sure you get the kombucha lab from D2L if you haven't already done that. All right, any questions about that, guys?
So should we just have the standardization procedure written out, like the part A and the procedure?
Yeah, actually, and all you really need at this point is the standardization part, because that's all we're going to do this week. Yep. If you want to work ahead, you can. Yeah, okay. Go ahead. What was that?
So like, could we organize this like we write out the procedure for part A, and then after that we like put down the data and the calculations for that, and then after that we write down the procedure for part B, and then we do part B next week?
Sure. Okay. I would have no problem with that.
Okay.
Yep, that's absolutely okay. All right, let me pop over to my notes here, guys. All right, so here we go. I kind of want to go back and look at that whole business of autoionization of water, because we're going to get some useful information out of that and some useful relationships. I think we kind of stopped with the idea of pH last time, and we sort of derived where pH came from based on that expression. But let me go ahead and throw it out here again to you, because it's just such an important thing to deal with. So
just to note, you're not sharing anything.
Nothing being shared? Yeah.
Nope.
Thank you. I forgot to do my screen share, I think. Let's do that. Thank you. That's good to know. There, now we should be. Thank you for letting me know. There we go. Now you see it?
Yep.
All right, awesome. Thank you. So let's start out with autoionization of water. So I've got this. You guys have this in your notes from last time as well. And this is where water actually acts as both an acid and a base. So we can let this water be the acid, this water be the base. Remember, we're talking about a Bronsted-Lowry acid-base reaction here, where the Bronsted-Lowry acid is going to donate a proton to the base. And the base, of course, accepts the proton. All right, so if that's going to be the case, we saw last time that we're going to make hydronium ion. That's an aqueous solution. And we're going to be left with hydroxide ion. Okay. So what you see is we actually have a conjugate acid-base pair here, right? Where you got water going to hydronium and water going to hydroxide, but then we can have the hydroxide reacting with the hydronium to give us 2 waters back. All right. And we said that this whole thing is governed by an equilibrium constant called the Kw. And we had a value of Kw at 25 degrees Celsius. We said that was 1.0 times 10 to the minus 14. Okay, so based on a recollection of what equilibrium constants mean, it tells me that this reaction proceeds very, very little to the product side. So water doesn't dissociate very well into its component ions. Okay, So the other thing we did was we sort of put together a little ice table here so we could figure out at 25 degrees Celsius what the concentration of each one of these ions actually is. Okay, so water, remember, doesn't show up in the equilibrium expression because it's pure liquid. So we put X's there for that. Our initial concentration of the hydronium was 0. Our initial concentration of the hydroxide was 0. The reaction has to go to the right so we can make some of those things. So my Q is actually equal to 0 here. And since Q is equal to 0, I've got to actually go right. So I'm going to go right by saying X and X. Okay. So now we're going to add down 0 plus X is X, 0 plus X is X. Now we put all this into the law of mass action, right? So remember what the law of mass action for this reaction looks like. Looks like hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. All that's equal to Kw, which is 1.0 times 10 to the minus 14. And remember, why doesn't the water show up in the denominator? Oh yeah, it's a pure liquid, so it doesn't show up in the law of mass action. All right, so now we plug in X's for both of those things. Okay, so we have an X there for hydronium ion. We have an X that goes in for hydroxide ion. That gives me an X squared, which is 1.0 times 10 to the minus 14th. Take the square root of both sides and you get 1.0 times 10 to the minus 7th molar. And that's equal to the hydronium ion concentration at equilibrium. And it's also equal to the hydroxide ion concentration at equilibrium. Okay, and that's kind of where we ended last time. And we gave a real quick explanation of how we could define this as being the neutral point on the pH scale by giving you a preliminary definition of pH. But here's another thing you can do with this. Before you even get to pH, if somebody wants to know, for example, what the concentration of the hydroxide ion or the hydronium ion in an aqueous solution is, here's your relationship, okay? It's this. I can go right back to the law of mass action. H3O plus times hydroxide is equal to 1.0 times 10 to the minus 14th. So now I can use this relationship to determine how much hydroxide or hydronium is going to be present in any given solution, okay? So let's look at an example of how we might do this. So let's say I've got, let's just take something really simple here. Let's say I've got NaOH, which we know is a strong base, right? Now, we know what's going to happen. That's going to dissociate 100% because it's a strong base to give us sodium ion. And it's going to give us hydroxide ion. Those are both aqueous. Now let's say, for example, I've got a 1.0 molar solution of sodium hydroxide. If that dissociation happens 100% to the right, well, then I know I've also got 1.0 molar of sodium ion, and I've got 1.0 molar hydroxide ion. That makes sense to everybody? It's just
Yep.
a simple dissociation. All right, so I could ask the question, what's the hydronium ion concentration in this solution? Now, would you expect it to be high or low? So is hydronium an expression of acidity or basicity?
Acidity, so it would be really low.
You'd expect it to be really low to non-existent because this is obviously a strong base at a relatively high concentration, dissociating 100% into solution. But I could calculate what that hydronium ion concentration would be based upon my equation up there from the law of mass action. So let's just solve that equation. So the hydronium ion concentration is equal to my Ka, 1.0 times 10 to the minus 14th, divided by my hydroxide ion concentration, right? Which is 1.0 molar. Now I know I have to get a molarity out of this, so don't worry about the units because we don't put units on equilibrium constants, but we know we have to get a molarity out. And the math is easy here. You get 1.0 times 10 to the minus 14th. Now that becomes a molarity of hydronium. Okay, and that's pretty much exactly what we would have predicted, right? Because we have a really basic solution with a high concentration of hydroxide ion. So that should thereby force the hydronium ion concentration to be very, very small in solution. Okay, so that's pretty much exactly what we would have predicted. Now, but the point is, I've got a means through an equation that relates those two ions through a constant of calculating what the concentration of one of them is if I know the other. Okay, so that's actually a very useful thing to be able to do. All right, any questions about that? So this kind of brings us back to the pH scale, guys, which we sort of introduced last time. So notice here, if I compare these two concentrations that I have of ions in the solution, notice that I have 1 molar concentration of hydroxide, but I've got 1.0 times 10 to the minus 14th molar concentration of hydronium ion. Notice that both ions are present in solution, but at vastly different concentration ranges. Okay, my hydroxide is high, but my hydronium is exceptionally low. Okay, everybody see that? So this brings up the whole business of why we would want to work with the pH scale in the first place. Because I can have a solution such as this, where I've got such vastly different concentrations of these ions, that it might make sense to sort of try to bring that into a more reasonable scale, if you will. Okay, and that's what pH does for us. Now, we said last time that the definition of pH is the negative base 10 log of the hydroxide, or sorry, the hydronium ion concentration. That's H3O plus. Okay, and that's another thing we're going to learn. Anytime I put this lowercase p in front of a quantity, that tells me I'm going to take the negative log of that quantity. Okay, so for example, if I put a px, what does that tell you to do?
Negative log of the concentration of X.
So it tells me the negative log of whatever X is. If it's concentration, we'd use a concentration X there. Okay, so if a pH is the negative log of the hydronium ion concentration, you guys tell me what a pOH would be.
Negative log of the hydroxide concentration.
That's it. So we do this all the time. We put this little p in front of things to take a quantity that might be very, very tiny, for example, and turn it into something that is a little more reasonable. Because what does a log do? It compresses a number. Take something either really big or really small and compresses it into something around 1, maybe in the range of 1 to 10, or 1 0 to minus 10 or something like that. So logs compress. So here's another one we see all the time. What if I said that I wanted to take a pKa? What do you think that would be?
Just a different dissociation constant. So yeah, just for something that's not water.
Okay, yeah, that sounds right. Because for water, I could have a pKw, couldn't I? So let's do that one. Because you see these all the time. But what does the little p tell me to do to that quantity?
Take the negative log of it.
Yeah, so pKa would be the negative log of the Ka, or the acid dissociation constant for some weak acid, right? pKw is a very specific one. That's telling me to take the negative log of the Kw. And that one we can do, right? That would be the negative log of 1.0 times 10 to the minus 14th, wouldn't it? And that turns out to be 14. So see how I took a really, really tiny number and sort of compressed it down to something around 10. So that's actually what taking that negative log quantity does for us, right? Because if we talk about the range of acidity or basicity that we can have in a solution, we've already seen that it can be vastly different over orders and orders of magnitude, right? from maybe 1 all the way down to 10 to the minus 14th. That's what? 14 orders of magnitude. So it makes a lot of sense to be able to compress those values or those concentrations into numbers between, say, 0 and 14. Okay, and that's kind of what the scale is doing for us. Since we're doing them all here, what would a pKb be, do you think? Well, first of all, what does the P tell us to do?
Take the negative log.
Okay, and take the negative log of what quantity would be a KB. Remember what a KB is from the last time, guys? That's a base dissociation constant. So that's the equilibrium constant associated with the dissociation of a weak base like ammonia. Okay, so we do this all the time. We put this negative log in front of really tiny numbers to compress them to something more logical or reasonable. And that's helpful when we make comparisons between these things. Okay, so again, just kind of going back and reviewing the pH scale, think of it as a number line, right? We know that the midpoint is 7, and now we know why the midpoint is 7 on the pH scale, because that's the neutrality point, right? If I go back up here to my original dissociation of water, right? If you look up there, my concentration of the hydronium ion is equal to the concentration of the hydroxide ion. So X is equal to X, right? They're the same thing. That's what we said right here. So those ions neutralize each other, don't they? So there isn't an excess of either one of those ions in solution. So if there's not an excess of hydronium or hydroxide, that puts me at the neutral point of the solution, doesn't it? And the neutral point, if you take the negative log of 1.0 times 10 to the minus 7th is, guess what? 7. Okay, so that's my neutral point. So neither the hydroxide nor the hydronium is in excess there. And I could have a pH of roughly 0, and I could have a pH of, say, 14. That's the normal range we think about. And we said last time, if I have a pH lower than 7, that means I've got an acid in solution. If I have a pH higher than 7, that means I've got a base in solution. So what does that mean in terms of the ions? Well, if I have an acid in solution, that tells me that hydronium ion dominates over the hydroxide ion, right? There's going to be a higher concentration of hydronium than hydroxide. But if I get to a pH above 7, well, then it's the opposite situation. In that case, the hydroxide ion is going to dominate. So in the case of an acid, the hydronium ion concentration will be high and the hydroxide ion concentration will be low in the solution. And if I've got a basic solution, the hydroxide ion concentration will be high and the hydronium ion concentration will be low. And that's pretty much what we found out in that little example, didn't we? What did we do up here? Where we took a strong base and dissociated it. I had a high concentration of hydroxide ion, and that forced the concentration of the hydronium ion, which is right there, to a very low value, right? And where am I in that situation? Well, I could figure out the pH, right? And we did. What is the pH of that solution? How would I calculate the pH of that solution? Right? It would be negative log of 1.0 times 10 to the minus 14th. What does that give us? Well, we just did that one down here for pKw, and that's 14. So that's where we are on the pH scale. All right, does that kind of sort of make sense to everybody in terms of what's happening on the pH scale?
Yep.
All right, no questions about that? All right, and now we know that we have a relationship between hydronium ion and hydroxide ion, so that if I know one, I can get the other, and I can do that for any point along this pH scale. All right, so that's kind of my definition of the pH and pH scale. All right, so what's next? Well, now we actually start talking about acids and bases for real. And we've already touched on this. Well, we can talk about acid and base strength, okay? So this is where we talk about strong versus weak. So if I have a strong acid or base, doesn't matter which, what do we say about it? What have we said about every strong acid or base we've talked about so far in terms of its dissociation?
It dissociates 100%.
Yeah, it goes 100% to the right. So if we say it's 100% dissociation, what does that really tell us about the equilibrium constant for that reaction? Is it really big or really small as I write the reaction?
Really large.
Yeah, huge K. Huge K. Okay, so the reaction is being forced way, way, way to the right. Okay, to the point that for all intents and purposes, we can say that the reaction is going 100% to product. Okay, and that's indicative of a very, very large equilibrium constant. Now, what if I have a weak acid or base? What do I know about the dissociation of a weak acid or base?
It dissociates partly, not fully, to 100%.
Yeah, so it's going to dissociate somewhere less than 100%. Good. Now, what this tells me is that now I've got a distribution of reactants and products in the solution, right? So now it tells me that equilibrium matters. It tells me that equilibrium matters. So when I run into a weak acid base situation, I'm going to have to apply equilibrium concepts here. So we know what that means. It means ice tables and things like that. Okay, but if I have a strong acid or base, I don't have to worry about it because I'm going to assume that reaction goes essentially 100% to the right. So I'm converting all of my reactant to product. So I really don't need that double arrow anymore. Okay. Now, the real question then is if we're talking about strong acids and strong bases, what are some of them? Okay, so what are some common strong acids, for example? It's nice to kind of recognize the ones you run across. You guys know any that we can just sort of list off?
Hydrogen chloride,
What's that?
HCl.
HCl. That's hydrochloric acid. Okay, what's another one?
Hydrofluoric.
Hydrofluoric is actually weak.
Sulfuric?
Yep, sulfuric in its first deprotonation is strong. That's actually a diprotic acid. Notice that it has two hydrogens out front, so it can actually donate two protons. So we call that a diprotic acid. The first deprotonation is strong, the second is weak, but we consider it a strong acid. What's another one?
Is phosphoric acid one?
Phosphoric is actually weak and it's triprotic,
Okay.
but it's actually weak in all three dissociations. Good guesses then. How about this one? Nitric acid is strong. And then some of the other mineral acids besides HCl, like hydrobromic and hydroiodic, those ones are actually strong as well, but not HF. And then the last common one is perchloric acid, HClO4. So that's kind of your list of strong acids that you would normally run across in the lab. There are other ones as well, but these are the common ones that you run into. Okay, so it's always interesting, like when I teach dynamics, when I'll have some sort of an acid-base dissociation problem like this, and I'll ask the students to calculate the hydronium ion concentration when a 10th molar solution of HCl dissociates. And invariably somebody says, well, I can't work the problem because you didn't give me a Ka for it. And I always look at them and say, do you need a Ka for this? And they always look back at me very quizzically. Do I need a Ka for HCl?
No.
No, because we assume it dissociates 100%. You're not going to find a Ka tabulated for HCl. That's why, because it's a strong acid. Okay. Now, what about strong bases? And again, this isn't by any stretch a comprehensive list of them, but basically these are going to be your group 1A hydroxides. And your soluble group 1B hydroxides. Okay, so when I say group 1A hydroxide, what am I talking about? Well, I'm talking about something like NaOH, KOH, this kind of thing. Okay, and by the time you get to your group 1B hydroxides, or that should be, sorry, group 2A. Sorry, I'm way off base on that. 2A hydroxides. Those are things in the second column, right, that are actually soluble. So I think those are the ones that are further down, like strontium hydroxide. Things like that, okay? So those are going to be your common strong bases, and they're going to be your hydroxide bases. So it's easy to identify them. All right, so that's sort of where we are with that. Now, what about the weak ones? Again, a lot of this is about just identifying things. Turns out that most of the weak bases, not all of them, but most of the weak bases tend to be what we call carboxylic acids. As a matter of fact, the carboxylic acid group is one of the organic functional groups that you learn when you take organic. And basically it looks like this. All right. So usually in organic chemistry, you could have R, which is just some, for example, alkane group, like a CH3 or a CH2, CH3 or something like that. And then what this is attached to is the carboxylic acid group, which looks like this. Okay. Now, if you look at that thing, you can see where the acidic hydrogen is going to be. It's that hydrogen hanging off of that terminal oxygen there. Okay. Now, the real question is, well, for that hydrogen to be acidic, it means that oxygen has to let go of it pretty easily, right? In other words, that bond between that oxygen and hydrogen has to be fairly weak. Okay. If it were strong, then this thing wouldn't be a very good acid, would it? So in a situation like this, I'm taking advantage of the fact that that bond is weak. Now, what happens when this thing dissociates? And this happens with pretty much all carboxylic acids. This is what you get. If I show it as a dissociation reaction just occurring in water. That's an oxygen, sorry. That should be a hydrogen there. I don't know where I'm going today. All right, let that combine with water. So this guy's going to be the acid, water will be the base, right? So what I'm going to get is hydronium ion. And then I'm going to get what we call the carboxylate ion. And those are just electron pairs. And that thing now takes on a negative charge. Okay. So that's what we end up getting. And that's typically what we're going to have when any one of these weak acids that happens to be based on a carboxylic acid group dissociates. All right. So if you look at this, if the original acid is the acid, the water's the base, well, then the hydronium ion must be my conjugate acid. And the carboxylate ion that we make must be the conjugate base, right? Because if the reaction goes in reverse, and I'll actually show it as the double arrow here. Now the hydronium is going to protonate the carboxylate ion to go take us back to carboxylic acid and water. Okay, so you can see how that reaction runs in reverse as well. As I mentioned, this is going to be governed by a Ka. That's an acid dissociation constant. That's the equilibrium constant for that reaction. All right, so that's what ends up happening. Now, the common one here that we always run into is this. It's acetic acid. is sort of the, and we've already looked at acetic acid as an example of that. The formula for acetic acid is this, HC2H3O2. If I wanted to actually draw it out, okay, what would it look like? Okay, it would look like this. I've got a carboxylic acid group. And then what I would have this attached to is a CH3 group, or a methyl group as we call it in organic chemistry. So that's actually what the Lewis structure of acetic acid would look like. So you can see the C2s there. There should be 4 hydrogens altogether and 2 oxygens. So there it is. Okay. So normally though, the way we write this is if we write this reacting with water, okay, we know that the acetic acid is the acid and the water is the base. So we pitch that acidic hydrogen, which is that guy right there, over to the water to make the hydronium. And we make the acetate ion, which is C2H3O2. Those are all in aqueous solution. A lot of times once we get used to doing this, I'll leave the AQs out because they're sort of understood. But if I have like a liquid, a solid, or a gas, I'll put that in. But anything else is going to have an understood AQ on it. Okay. And what does the acetate ion look like? Well, the acetate ion is going to look like this. And I've still got the CH3s out here. Okay. So does that seem reasonable to everybody? And like, again, we can say, okay, the acetic acid is the acid, the water is the base, hydronium has to be the conjugate acid, and the acetate ion has to be the conjugate base if we want to talk about the reverse reaction. And again, this is going to be driven by a Ka. And I think I told you guys last time what the Ka for acetic acid is. I think the Ka turns out to be like 1.75 times 10 to the minus fifth. I think that's what I have written down for it. So what does that tell you about acetic acid? Is it a very strong acid or actually quite a weak acid?
Fairly weak.
It's going to be very weak because, again, we're not going to make a whole lot of product here. So in other words, we'd expect the hydronium ion concentration to remain quite low because we're going to get very little dissociation of the acid. All right. So is this sort of qualitatively making sense to everybody? And like I said, a lot of these acids are these organic carboxylic acids, these weak acids. Now, the other thing to recognize is that in the back of the book, there's a whole table of Ka values for these acids. Okay, and if you go back and look, it'll often show you the structures of the acids as well as the formulas. So you can see that actually most of them are going to be some variation on these carboxylic acid type acids here. All right. Now, what about weak bases? Most weak bases are what we call organic amines. Not all of them, but a lot of them are, okay? Now, what is an organic amine? Well, an organic amine is going to take this general form. It could have, for example, an R group, which we said could be something like a CH3, attached to a nitrogen, attached to, say, for example, a hydrogen or a hydrogen. And if we track our Lewis structure, what we're going to see there is that we're going to actually have a lone pair of electrons on the nitrogen. Now, why is that important? Well, that's important because now that lone pair of nitrogens, or sorry, that lone pair of electrons on the nitrogen could be used to grab a proton from an acid, right? And if that happens, then I'm going to protonate the base and turn it into a conjugate acid. So in this case, we might have a Kb associated with this. Now, one very simple example of this that we talked about before, and this is a specific one, is ammonia. Ammonia is NH3. So it's sort of the simplest organic amine because the R group here is actually just a hydrogen. All right, but notice how it still has essentially the same basic formula. So if that's ammonia or NH3, I could look up KB for that. So that's a base dissociation. All right, and it turns out the KB for this is very close to the Ka for acetic acid. It turns out to be 1.76 times 10 to the -5th. Okay, so in terms of size or magnitude, it's really about the same as the Ka for acetic acid. Okay, but now what is the reaction that's taking place here? Well, it's NH3, and again, we've seen it before, reacting with water. Okay, in this case, the NH3 is the base, water is going to be the acid. So remember, the acid does the protonating of the base. So one of those hydrogen ions is from the water is going to be pitched over to the NH3, and the NH3 can accept it because it has that lone pair of electrons up there on the nitrogen. So I can make a bond there to make ammonia. So now what I'm going to get, and again, this is defined by that Kb, is I'm going to make the ammonium ion. So the base gets protonated. And I'm going to be left with hydroxide ion. I think we saw that reaction last time. Okay, so the ammonium now becomes the conjugate acid if we're thinking about the reverse reaction, and the hydroxide ion becomes the conjugate base. And again, if you looked at this in terms of formulas, here's what the ammonia looks like. And then the ammonium, which is the conjugate acid, is going to look like this. And that's a polyatomic ion that you guys all know. Okay? Questions about that, guys? Everybody good?
Sounds like it.
All right. Hearing no further questions, as they say. Now, here's another thing that we can do. I'm just going to go back to, and this is going to give us another important expression that is useful down the road, is let's just look at a generic weak acid. All right, and I'm just going to write it in terms, and you'll see this happen a lot, where I've got HA as my generic weak acid. Okay, so A is sort of the anion of the acid. That's why we use A for that symbol. And that can react with H2O, which is my solvent. It's also my base. So this is my acid. This is my base. You guys know what the products are going to be. You're going to make hydronium ion. And you're going to make the anion of the weak acid, which is A1 minus. So there's my conjugate acid, and that's now my conjugate base. All right. And then we can do in general terms a weak base dissociation. So in this case, what we usually do is you just use B for base. And a lot of times we'll put just an electron pair on it to show that it can accept a proton from the acid. So again, these are just my generic terms here. So it's going to react with water. Okay, so now the base is the base, water is the acid. Again, that's going to be a Ka. This guy will be a Kb. So what's going to happen? The acid's going to protonate the base. So I'm going to make Hb plus. And I'm going to be left with hydroxide ion. So we often write these things in terms of these generic reactions like this. So now Hb1 plus becomes my conjugate acid, OH minus becomes my conjugate base, okay? So we can write these things in such a way, and we can relate conjugate acid base pairs if we wish. All right, so those are the generic forms, more or less, of the reactions I just wrote above for you. All right. Now, another problem that arises. So we talk a lot about Kas and Kbs, right? And we know what those represent now. But if you go to the appendix in the back of the book, you're going to find a whole bunch of Kas back there for weak acids. And then you'll say, okay, I can go to the next appendix and find a bunch of Kbs for weak bases. But guess what? There isn't an appendix for Kbs. So then you start wondering, well, how do I find out, how do I get a Kb if I need one, right? If there's not an appendix that has them in there. Well, as it turns out, for any conjugate acid base pair, I can relate a Ka and a Kb. So we're going to write that. This is really important. So in other words, if I have my generic weak acid dissociation, HA, okay, let's just let that happen. We'll go to H2O. We know what it looks like. We know it's governed by a Ka here. We know what we're going to make. Seen this reaction a zillion times. And you're going to get the anion of the acid. Okay. But remember, I've got a conjugate acid base pair here. Remember what it looks like. HA is the acid, water is the base, H3O plus is the conjugate acid, A minus is the conjugate base. Now, what if I took that conjugate base and I let it dissociate by itself in water, by its own reaction? Okay, so what if I did this? We know that's base, right? Because it's an anion of a weak acid, so it's got conjugate base properties. So if I took it by itself and put it in solution, it would be a base. Let it react with water. Oh, we know what would happen. That's now the base. Water becomes the acid. That's going to be defined by a Kb for that base. What do we make? We make hydroxide ion, right? And we also make the protonated form of the base, which is HA. Oh, that looks like the original acid I had in the first equation, doesn't it? Okay, so the hydroxide is now my conjugate base and the HA is my conjugate acid. And that makes sense. If HA is a conjugate acid, if I had HA by itself and put it back in liquid solution with water, it's going to act like an acid. All right, so here's the interesting thing about this, guys. Let's take these two reactions, which involve conjugate acid base pairs, and let's add them up, just like we know how to add reactions when, for example, we do equilibrium problems. Look for things that can cancel on both sides. Oh, I see an A1 minus that I can cancel out. Oh, I see an HA I can cancel out. What am I left with? Well, I'm left with this. I've got H2O, liquid, plus H2O, liquid, dissociating to, it looks like H3O plus, and hydroxide ion. Is that a reaction you guys have seen before?
Absolutely.
Yes, that is the autoionization of water. And does it have a K?
Yes.
It's called KW, right? Oh, and that has a value, doesn't it? That's the 1.0 times 10 to the minus 14th one. Now, here's the deal. We just added two reactions together. Now, remember, if I add reactions together, what do I do to the equilibrium constants? If I want to get the equilibrium constant for the bottom reaction, the KW, how do I do that in terms of the K and the KB?
Multiply Ka and Kb.
Yeah, you multiply them. Remember, when we add reactions, we multiply equilibrium constants. So now look what happens. I can say that Ka times Kb is going to equal to Kw, which we know is equal to 1.0 times 10 to the minus 14th for any conjugate acid base pair, right? Because what am I talking about here? Look at those two reactions up top. We're talking about conjugate acid base pairs. HA, the acid, dissociated to give me A1 minus the base. A1 minus the base, which is now the conjugate base, reacts with water to give me the conjugate acid back again. That's a conjugate acid base pair. Okay, so this is true for any conjugate acid base pair. So what have I got now? I've got a means of being able to get a Kb for a base if I know what the Ka of its conjugate acid is. Oh yeah, and remember, if I know the acid form, I can look that up in the appendix and get a Ka for it, can't I? So now I've got a direct way of getting a Kb from a Kw and a Ka. So to get the Kb for any base, as long as I know the conjugate acids form, I know that's going to equal to Kw divided by Ka. Okay, I could also write that as 1.0 times 10 to the minus 14th over the Ka of the conjugate acid. All right, so that's very, very useful to us, extremely useful to us. So for example, I don't have my book with me, but I'm just trying to think of how I might use this. So let's say I wanted the Kb for ammonia. Anybody have their book handy? I don't have mine here. Anybody got a
I
copy
got
handy?
mine.
Perfect. Look up that the Kas are over in what, Appendix B, is that correct?
They should be, yeah.
Yeah. So here's the deal. Let's just say I want the Kb for ammonia. Now, I already told you guys more or less what it was, but let's just say I didn't do that. You can look around in there and you probably won't find it in a table there, okay? So tell me how we would find it based on what you have available to you. Well, I got an equation for that, right? We know that Kb is going to equal to Kw divided by Ka, but what Ka am I going to go look up?
Ammonia or yeah, ammonium.
Ammonium, it's going to be the acid form of NH3, right? So what I need is the Ka for the acid form of ammonia, which is going to be NH4 1 plus. That's the ammonium ion. Now, is that in there?
Yeah, I have it.
Okay, what is the Ka for that?
It is hang on. It is 5.69 times 10 to the negative 10th.
Okay, good. So now, could I calculate the value of Kb? I'm sure somebody has a calculator. Let's go ahead and do it. So the Kw is what, 1.0 times 10 to the minus 14th. And I'm going to divide that by the Ka for ammonium, because that's the acid form. That's 5.69 times 10 to the minus 10th. Anybody want to just chow that out and see what you get?
1.9 times 10 to the negative 5th.
And that's pretty close to the value I gave you. I think I gave you like 1.78 or something like that times 10 to the minus 5th. 1.78 is about 1.8, and this book is using 1.9 times 10 to the minus 5th. So that's close enough. Okay, so you can see how I was able to calculate a Kb, even though I didn't have one for ammonia. But I could do it because I know what the conjugate acid form of ammonia is. That's the ammonium ion, and I can look that up in the Ka table and use that to get a Kb. Everybody see how I did that? So even when you get to dynamics and you start doing this, you'll actually have a Kb table as well as a Ka table in dynamics, but what you're going to find is that the Kb table is really short and the Ka table is really long. So there are going to be a lot of situations where you aren't going to be able to actually find the Kb for the base you want, but you can find the Ka for the acid form, the conjugate acid form of that base, and then calculate a Kb for the base that you're looking for. This is how you do it. Okay? But the important thing to remember here is this only applies to a conjugate acid base pair. So you have to be good at identifying conjugate acid base pairs. All right. Any questions about that, guys? So next time where we're going to go with all of this is we're going to actually start to calculate some pHs of some strong and weak acids and bases. Okay, so that's kind of the next set of calculations we're going to look at when we meet again on Wednesday. All right, everybody clear on what you need to do for lab tomorrow? All right. If there are no other questions, I think we are good. And I will see you guys tomorrow at 5.
All right. Thank you.
You're welcome, guys. We'll see you then.